All right. Are you guys ready?
No.
So a couple of things. First of all, you should be able to work through all of the chapter 3 homework. Okay, there's 3 models that we looked at, 2 of which are linear, namely the basic population model and Newton's law of heating and cooling. Of course, we talked about why Newton's law of heating and cooling really is just the population model, again, in disguise. So really there's one model we talked about, right? Just in terms of the linear models, okay? And then we looked at the logistic model, okay? That was the one nonlinear model we looked at. Now there's going to be some problems that you have to work through where you will have to kind of think a little bit about how to turn the model into the logistic model. Well, you might have to do some kind of U substitution or something like that. Does that make sense? But I've intentionally given you those. The book doesn't really talk about that per se, but I think it's a good skill for you to have. Just say, oh, if I put U equal to this, I can turn this into something that looks like a logistic model, and then I can apply the logistic situation to it. Yes? So I'm going to let you kind of work through that as you go through the homework. Yeah, we're going into chapter 4. Now, the first section of chapter 4 is kind of a grind, okay? It's definitely my least favorite part of the course, and that's sort of a bad thing for me to say out front. Just because if I'm kind of grinding through it, you're going to be grinding through it as well. But I just want you to be prepared that this section is pretty big, and it's kind of laden with theoretical things, okay? But they're all things that are important for our flourishing later on. We have to kind of go through it so that we can know for sure that the things we are doing are producing good results that we can rely upon, and that we're not missing anything, okay? So it's just kind of the nature of the beast. I'll try to make it as lively as possible. Hopefully you guys won't be falling asleep. I'll try not to fall asleep myself. But the first section of chapter 4 is like, if I'm looking at my paper typed out notes for myself, I have about 90 pages of notes, but this constitutes about 10. So it's a fairly substantive piece of the notes. Yes, so it's like 11% of my notes are this one section. It is important material though. Believe me, I thought carefully about it, and I was like, man, how much of this stuff can I kind of skip over? And the answer was basically none of it. I kind of have to just go through it in order for you to be able to do the stuff later on with great zeal and confidence, okay? I'm also, the way I'm going to state some of the theorems that we'll run into are going to be slightly different from what you see in the book, okay? They're going to be a simplified version of what you see in the book, okay? So with all those caveats aside, just know that we are trying to lay the foundation for how to deal with higher order linear differential equations, especially not nonlinear. Nonlinear stuff is just really gnarly, okay? You already saw that even just with the logistic model, and that thing was like baby food in the realm of nonlinear equations, okay? And that was still pretty hard. These things can just get really bad really fast if they're not linear. So we're thinking almost exclusively about linear higher order differential equations, okay? Again, last time we finished with this example on COVID spread on campus, right? And now we're going to start talking about higher order differential equations in chapter 4. Now, again, what if I say higher order differential equations? I just want to make sure that we're all on the same page. What do I mean by that?
That could mean like having second order.
Okay, well, what does that mean, second order?
That means like the derivatives are 2 a power.
Yeah, that
Right?
no, not that the derivatives are 2 a power.
The second derivative.
Yeah, the second derivative like maybe appears. Like if I had to, okay, the order of a differential equation is by definition the highest derivative that appears, yes? So if I say that a differential equation is order 4, that means the highest derivative appearing is the 4th derivative. Yeah. Okay. So we're going to be looking at higher order differential equations because we have already slain the beast of first order differential equations. There is nothing we don't know how to do. We're bored and we need something more challenging at this point. In chapter 4 is where we start to do that, develop lots of other techniques. Okay. And again, this section, which I call preliminary theory on linear equations, is going to be somewhat of a grind, but just bear with me, okay? So do you remember like what a generic linear equation looked like? What does a generic linear equation look like? Remember? What's the rule for it to be linear?
Derivatives aren't raised to a power.
Yeah, you can't be raising derivatives to power, like, you know, whatever the order of the derivatives are, you can't be raising them to powers. What else can't you do? Yeah.
Multiply 2 derivatives.
Yeah, you can't be multiplying various derivatives of y together. Can I have functions of x sitting next to the derivatives though? Sure. Okay. But really, those are the two main stipulations. Okay. So a generic nth order linear equation looks something like this. We kind of wrote this down before, if you will recall. Okay. So a and x, nth derivative of y with respect to x, plus a n minus 1 of x. Notice that these indexes on these little functions match the order of the derivative, yeah? And these little functions of x can all be different functions. They don't have to be the same function. But I want to put an index on those functions that matches the order of the derivative that's there. This guy is an nth order linear differential equation, and we're going to turn it into an IVP. Now, just to make sure we're all on the same page, what does IVP stand for? Initial value problem. Now, if we had a first order linear differential equation, how many initial conditions did we need? This isn't a trick question. How many initial? 1. We just need to know what y was at some x value, yes? So for a first order linear differential equation, first order, we needed 1 initial condition. If we were doing a second order linear differential equation, how many initial conditions do you need? 2. Okay. Turns out what you're going to need to know is, remember, like in the first order initial value problem, like we needed to know what y was at some number x0, some x value x0, yes? And that basically told you a point that the graph y of x had to go through, yes? When we have a second order differential equation, it's not enough just to specify a point that you go through, like y of x0 equals some y0. You also have to specify what the slope is there. So you need to tell us what y prime at x0 is at that thing as well. And then you kind of move up the line. If you have a third order differential equation, you need to know y at some x value. You need to know y prime at that x value. You need to know y double prime at that x value. You need to specify a point, the slope, and the concavity at that point to uniquely determine the thing. Yes? Okay. So the number of initial conditions is going to be equal to the order of the differential equation itself. So that said, we now are going to have a bunch of initial conditions. Y of x0 equals y0. That's kind of like what we had before, yes, for a first order one. But now we also need to know y prime of x0. And that could be some other number, y1, like the slope of the solution curve at x0 could be some other number, y1. And look, I'm telling you that instead of writing prime, because whose notation is that in calculus, the prime notation? That's Newton. And unfortunately for Newton, that starts to get fairly gnarly once you get beyond like the second or third derivative or so, right? You just have to write a massive number of tally marks, especially when you get to, you know, 5th, 6th, 7th derivatives. So the way Newton solved that problem was by abbreviating the number of tally marks with just a number inside of some parentheses. Yes? And so as not to confuse it with the power, like raising that function to a power, he put it in parentheses. So instead of writing y prime, you can write y to the parentheses 1 of x0 equals some number y1. That means the first derivative at x0 equals some number y1. Okay, same thing here, y prime prime at x0 equals y2. You can replace the prime prime with like a parentheses 2, okay? And so on and so forth. Where does this madness stop? Well, it stops as soon as I have in initial conditions, okay? And since I started with like the 0th derivative, yes, that happens once I get to the n minus first derivative of y evaluated at x0. Okay, that's going to be some number y sub n minus 1. So in other words, there are n initial conditions here that we need, okay? N. Does that make sense? Hopefully, I mean, I know there's lots of letters flying around here. But the two things I want to point out is when we have an nth order linear IVP, we need n initial conditions. Just like in a first order IVP, we needed one initial condition. Now we need n if we're in order n linear differential equation. The second thing I want to point out is the following. Notice where are all those derivatives evaluated at in the initial condition? X0, the same x value. The same x value, yes? You need to specify all of those things at a singular x value. The y values can be different, or the various derivatives can be different at that x value, but you need to be dealing with the same x value. If you really want to like do a PhD in differential equations, then let the x value differ, because then you're going to start getting like multiple solutions. That's something called a boundary value problem, not an initial value problem. Initial value problem, you use the same x value for all of your initial conditions, yes? Of course, the y values for the various derivatives could be different in theory, okay? So a couple of notes. So what I just said, all initial conditions are evaluated at the same exact x value, x0. If we did allow for different x values, this would be called a boundary value problem. And you can go talk to Dr. Wright about that. That's the sort of thing he loves, okay? Boundary value problems are extremely difficult and kind of slippery. Like you'll think you'll have it and then it'll go whoop, and it'll slip out from your grasp. I'd be like, oh man, I'm finding other solutions now. That is where I allow different x values to go in there for different derivatives. Okay. I think you'll have some problems in your homework from chapter 4 where you get to play around with some really, really, really simple boundary value problems. And you immediately realize, oh man, I could see how this could really get out of hand in a hurry. Okay. All right. Are you guys ready? We had like a IVP theorem, didn't we? The IVP theorem told us that we basically had a unique solution to an initial value problem. Yes, if certain things were satisfied, right? Remember that? The so-called IVP theorem, that's where we like drew that little box. We said, oh, here's the initial condition, x0, y0, yes. And we said, if we have a little bit of elbow room around that point, then there is a unique solution to the initial value problem. Remember that? Here, it's not so easy to draw a picture because the picture would actually live in like, the picture would live in like in-dimensional space, something that we can't really visualize. Is that? No, I know that doesn't make sense, but it does, okay? It lives in higher dimensional space. You can't like draw a picture of what's happening here anymore. So what I'm going to do is I'm going to capture the essence of what the nth degree linear IVP theorem says. It's basically the same, it's saying the same thing in a different way. But we're just not going to have a picture that we can look at, okay? Okay? So here's what it says. Suppose that So this is the nth order IVP theorem. By the way, the nth order IVP theorem subsumes the one that you had before. Remember that was the one where you had like the partial of f with respect to y and all that stuff. Okay. This thing is going to say that and more. It's going to apply to even higher order derivative, or yeah, right, higher order IVPs. So suppose that all of those coefficient functions, okay, these guys right here, all the way up. By the way, these are actually literally called the coefficient functions. So these guys right here are called the coefficient functions. Coefficient functions. Okay, because they are the coefficients of the various derivatives of y, yes? Suppose that all of those coefficient functions are continuous on the interval I. Okay, that just means they're nicely behaved. There's nothing weird going on. If x0 is any point in the interval on which those things are continuous, then a unique solution to the corresponding initial value problem exists. Also, there's one more stipulation. We also need the leading coefficient function, an of x. That's the thing that was sitting next to the nth derivative. We need that to never be 0 on the interval that we're looking at, okay? We need that thing to never be 0 on the interval that we're looking at. Now look at that. Look at this thing. That is not that difficult of a statement, is it? It's just saying all of the various coefficient functions are continuous on the interval. x0, the place that I'm evaluating all the initial conditions at, is in the interval. And the leading coefficient function, an of x, is never 0 on the interval. That's it. If all three of those boxes get checked, what do we know about the IVP in question? It will have a solution and it's unique. That's it. What more could we ask for? Now, I do want to remind you yet again that there's a logical trap that one can fall into here. Yes? So this theorem gives us conditions that guarantee a unique solution. Yes? If these solutions, or if these conditions fail to be met, does that mean that there is automatically not a unique solution? No, that's like sort of wrong logic. Remember we did the example with like the student scanning in or something like that, yes? Okay. Just because these conditions are not met does not automatically mean that we aren't going to have a unique solution. But there's no longer any guarantees. You might have 0 solutions. You might have 2 solutions. You might have 70 solutions. Okay, you might have 1 solution, but there's no longer any guarantees, right? Okay. Okay, questions so far? Questions? Any questions? Okay. Well, let's look at an example. Okay. Here's an IVP. Okay. What kind of an IVP is this? Okay, right here. So what kind of an IVP is this guy? Yeah, it's a right. So this is a third order linear IVP. Okay, which means that the highest order derivative that we see is 3. There isn't any nonsense going on with like multiplying y and its derivatives together. And I have how many initial conditions? 3. And they're given sequentially y at some number, y prime at that same number, and y double prime at that same number. In this case, what's our x0? Let's just make a couple of notes here. So we would have needed 3 initial conditions here. Let's make a couple of other notes. So note, what's our x0 here? What's the place that we're evaluating the 0th, 1st, and 2nd derivatives at? 1. What is A3 of x? Okay, just to be kind of clever here. What is the function of x sitting next to the third derivative? That's what A3 of x is. Yes, that's the coefficient function sitting next to the third derivative. So what function is it? 3. How silly. Yes? A2 of x is 5. A1 of x is what? -1. How interesting. A0 of x is 7. And g of x, which is the thing that's on the right-hand side, g of x is 0. Okay? All right. So what's true about all of those? What's true about all of those coefficient functions? I mean, where are those things? I mean, look at those functions. Those things are all like really pretty trivial. Yes, they're all constants for crying out loud. Yeah. Where are those all continuous? Everywhere. Yeah. Where, so like on the whole real line, -infinity to infinity, every single one of these functions is continuous. What about the leading coefficient function, A3 of x? Where is that non-zero? Everywhere. Okay. And finally, x0 equal to 1, that thing obviously lives in the interval from -infinity to infinity, yes? So look, what does the IVP theorem guarantees that there will be a unique solution? Already, we know that's true, yes? We know that there exists a unique solution by the nth order IVP theorem. Do you see what I'm saying here? Okay. We already know that's true just by looking at the 3 boxes that need to be checked. Are the coefficient functions continuous on the interval? Is the leading coefficient function non-zero on the interval? And does the place I'm evaluating the initial conditions, is that thing in the interval in question? Yeah.
What is the x not referred to?
The number that you're evaluating all of the initial conditions at.
So
Right? It's the number that you're evaluating all the initial conditions at. Okay. So x0 is 1 in this case, because I'm plugging in 1 into each one of these. Yeah.
Will we always assume the interval to be just negative infinity to positive?
No, not necessarily. We kind of just choose the interval so that it makes all those things continuous, and it makes the leading coefficient function not 0. And it includes the point we want to plug in. Does that make sense? A point x0. But in this case, it just so happens to be really easy to meet all of those requirements. Yes? The interval that we can use is -infinity to infinity. So before we even go to solve this thing, we already know that a unique solution exists, right? Can you think of a solution to this? Don't think too hard.
0.
0. Don't you see? 0 clearly satisfies this differential equation, because clearly if I put y equal to 0 here, all of its derivatives are 0, and that just kills everything, yeah? And moreover, if I plug x equal to 1 into the 0 function, it's 0. If I plug it into the derivative, I get 0. And if I plug 1 into the second derivative of the 0 function, I get 0. So y equal to 0 works. But by the nth order IVP theorem, y equal to 0 has to be the only solution. Don't you see? Yeah. Okay. Note that y equal to 0 works. So y equal to 0 is a solution to the IVP. Okay. Further, the coefficient functions are all continuous on the interval -infinity to infinity. Thus, by the nth order IVP, y equal to 0 is the unique solution to this. Okay, let me just say right here also, A3 of x, which is equal to, what was A3 of x? this thing is different than 0 on I. And x0 equal to 1 belongs to I. Sort of obvious things. Those are two things that we would have needed to be true as well. Yeah? Does that make sense? This is not like some kind of earth-shattering revelation. The only earth-shattering revelation is that there isn't anything else that could possibly work. That's what the IVP theorem does for us. Yeah? That's it. Okay? All right. What about this? Okay. What about this guy right here? Let's talk about this one. What are the coefficient functions here? First of all, this is okay. What is the order of this differential equation? 2. Okay. What are the coefficient functions? So the leading coefficient function, which is a2 of x, that's just 1. Yeah. And of course, a2 of x is never 0. Yes. Okay. What's a1 of x here? That's kind of interesting. A1 of x is the coefficient function sitting next to the first derivative. What is that? In this case, that's 0 all the time, right? That's okay though. That's still a continuous function everywhere, right? What about the a0 of x, the thing that's sitting next to the 0th derivative, or y itself? What's that? -4. What about the right-hand side function, g of x? 12x. Now, all of those functions are continuous where? Everywhere, yeah? They're continuous everywhere. How interesting. And the leading coefficient function, a2 of x, is never 0. And what does it look like our x0 is in this case? Like, what's the place we're evaluating all these things at? 0. Okay. And do I have enough initial conditions? Here. Yep. Because it's a second order initial value problem. I need I need the function evaluated at a point and the derivative evaluated at a point. Okay. Once again, what this is specifying is a place for the graph of the solution curve to go through. This means it would go through the point 0, 4. But this second initial condition is telling us not just a point that it goes through, 0, 4, but it's telling us what the slope of the tangent line is there. Does that make sense? This thing is also specifying the slope of the graph there. Okay. So this thing's looking pretty good. Before we even do anything, what do we know is going to be true? Right, there's going to be a unique solution. Yeah, there will be a unique solution. Okay. So this IVP has 2 initial conditions. x0 is 0, a2 of x is 1, a1 of x is 0, a0 of x is -4, g of x is 12x. While we will be able to solve this later, we can't right now. Okay, so unfortunately, we don't really have the tools to handle that right now. But as we've already noted, the nth order IVP theorem guarantees a unique solution exists because all these coefficient functions are continuous everywhere. And a2 of x equals to 1 is not 0 on that interval. And by the way, later, we will actually discover that the solution is this. Okay. Now, you wouldn't just stare at that thing and say, oh, obviously, y equal to 3e to the 2x plus e to the -2x minus 3x. That's obviously the solution to this differential equation, yeah? But later on, we will actually be able to predict what the form of the solution has to be, and we will actually be able to come up with that on our own. That's pretty amazing, yeah? But right now, we don't have those tools. But we knew there had to be a solution. That's the beauty of the IVP theorem, okay? So later we'll discover this, but that's not very exciting yet, but we can at least check that this is a solution to the IVP, can't we? How would I go about checking that this is a solution to the IVP? Yeah, just, take derivatives, plug in stuff, and just make sure it works, yes? So I can just verify that this is indeed a solution. And it's the only solution. So watch this. If you take the derivative, it's going to be 6 e to the 2x minus 2 e to the minus 2x minus 3. Why? Okay, how did I get 6 here? What did I apply? Chain rule, right? It's just 3 e to the 2x times 2 because of the chain rule. And then it's going to be e to the negative 2x times negative 2 by the chain rule. And of course, the derivative of negative 3x is negative 3. Okay? Take the derivative again. What am I going to get if I take the derivative again? Negative 12, or sorry, 12 e to the 2x, yes? What about this guy? Plus 4 e to the negative 2x, yes? We get this, right? And then we plug into the differential equation. The differential equation was y prime prime minus 4y is supposed to be equal to something. Y prime prime minus 4 times the original thing. Okay, so we take y prime prime minus 4y. Oops, that's weird. Y prime prime minus 4y. Y prime prime is right here. Minus 4 times y. Y is 3 e to the 2x plus e to the minus 2x minus 3x. We just distribute that negative 4, and lo and behold, stuff cancels. And what are we going to be left with? Like all the exponential stuff goes away, and all that's left is 12x, which is exactly what we needed. Okay, but that's not enough. It's not enough for this to be a solution to the differential equation. It needed to be a solution to the initial value problem. So we should also check that this thing satisfies the initial conditions, shouldn't we? Yeah. Does it? We need to evaluate this thing at x0 equal to 0, right? What do we get if I plug in 0 in for x? What would I get? If I plug 0 in for x, what do I get as the output? 3 plus 1 minus 0, which is 4. Yeah. So y of 0 is 4. Is that what we wanted for the first initial condition? I think so. Yeah, y of 0 was 4. And then we want the derivative at 0 to be 1. So I plug 0 into the derivative right there. Okay. So it's going to be 6 times 1 minus 2 times 1 minus 3. 6 minus 2 minus 3 is 1. Yeah. So does this thing satisfy the initial condition? Yes, it does. Okay, that's nice. Any questions on that? Any questions? I think that's kind of neat. We could predict ahead of time by using the nth order IVP theorem that we were going to have a unique solution. Yes. You don't know where this solution came from necessarily, but we will know that later on. We actually did find a solution for the first one, didn't we? Just by inspection, we were like, duh, y equal to 0 works, yes. But in general, we know that the IVP theorem tells us when we could expect to have a unique solution. This guy right here, again, isn't really that hard to actually find a solution for once we have a few more tools in our back pocket. That's what the content of chapter 4 is about, is giving us those tools so that we can actually come up with that solution on our own. Okay. What we will be talking about next is kind of breaking up a differential equation into two things. One is going to be the differential equation where we kind of replace the right-hand side with 0. We kind of deal with that. And the other thing is going to be dealing with the differential equation when we don't have 0 on the right-hand side. The first case is going to be called the homogeneous case. And the second case is going to be called the non-homogeneous case, all right? And we'll figure out how to sort out what's happening with each one of those things. And we'll sort of develop a general strategy to deal with these nth order linear differential equations. Okay? It's going to be kind of neat. Any questions? right. Well, that is basically all I have for today. We'll come back on Friday and get to it.